Thanks, Sarah. Thanks, Jess. And thanks, everyone, for coming. My name is Amy Jensen. Let me advance. I'm from Prince of Wales Island in Southeast Alaska. I'll show you where it is if you don't know in a moment. Yeah, so Prince of Wales is the island in the bottom corner of the picture. And I didn't have much familiarity with glaciers growing up there, but I moved to Juneau to go to college and quickly became enamored by the Mendenhall Glacier and the Juneau ice field and the Lemon Glacier. And I spent a lot of time recreating around these glaciers, but it wasn't until my senior year of college where I got involved with a research project with Jason Amundsen, studying the outburst floods that happen every year from Suicide Basin that you can see in this image. And I was really interested in using the math that I'd been studying to try to think about what might happen to these outburst floods over time as the glacier changed. And yeah, I eventually went to Montana, kept thinking about subglacial hydrology, really interested in how water moves through glaciers and how it impacts glacier flow, and eventually made it up here to work with Martin Trufer.
Thanks, Amy. Yeah, and just to introduce myself, I actually not one of the cool kids who grew up in Alaska, although I realized I've lived in Alaska longer than Amy has, so which my daughter pointed out, that's because you're old, Dad. So I grew up in Switzerland. This is actually the view from my parents' house. And we've always had a connection to glaciers there because of the proximity, right? They're small glaciers compared to Alaskan glaciers, but they're important. The picture in the upper right there shows a view from the glacier down towards the valley. And that's the sort of places where growing up we were told by our parents, oh, that's where we used to cross the glacier. So this idea of changing glaciers has been with me for a long time, but I never thought growing up that this is something you actually study. Culturally, if you look in the upper left, that picture is a picture of town from above. This is the driest area in Switzerland. There's not a lot of water. People traditionally in these small towns try to do agriculture, but the water came from the glacier creek in those little waterways that are pictured on the upper right there. And glacier change was a real problem for people, especially back in the Little Ice Age when the glaciers started advancing. They were impacting these waterways and therefore their livelihood. So what you do in a good old Catholic area like that is you make a promise to God that you'll be good if only the glaciers go away. So they build chapels. There's an annual procession that goes on to this day to pray for glaciers to retreat. That has worked extremely well. I think they should actually probably stop doing this now. Personally, I was kind of like Amy, a math physics kid, so I went on to university and started studying physics, and I figured I'm probably going to become an old guy who doesn't comb his hair and smokes a pipe. But at some point, I realized that in my studies that you can use these equations to describe really cool things like glaciers. And that really fascinated me, the fact that you can apply physics to learn about the Earth. So that's eventually what brought me to Alaska. I came for a PhD, planned to stay for 5 years. That was 30 years ago, but I think that's a common story here in Fairbanks. But let's get into the talk here. First of all, just before I start, we will talk about Greenland quite a bit today. And Greenland is in the news a lot today, and I just want to, and not necessarily in a good way, right? And I just want to acknowledge here that Greenland is an island that's not just a barren Arctic island. There's people there. There have been people there for a very, very long time that live there, that call it their homeland. It is a self-governing nation under the Kingdom of Denmark, but people very much, it's very much a self-governing nation. And one of the interesting things about being in Greenland, and as opposed to, say, Antarctica, is to see how the society in Greenland is sort of coming to terms with modern society, with a modern Western society, trying to develop the nation in a responsible way, in a way that's economically viable. And Greenland is going through really, really interesting times right now, and it's really been a privilege to witness that over time. I really like going there and seeing that. Lots of common things with Alaska. But let's get to ice sheets. We put centuries in the title because that sounded good with seconds, but I'm going to take an even longer sort of view and maybe get to millennia. So as most of you probably are aware of, in the modern day on the right there, the way it looks like if you look on the globe from the North Pole is that it's mostly land, except for if you look right now when it's snow. A lot of it is seasonal snow cover, but it goes away in the summer. Whereas, and the really only white part, except for the sea ice here, which is also largely seasonal, is the island of Greenland here, right? But this wasn't always the case. If we go back 18,000 years to the last glacial maximum, then almost all of North America was covered in ice, in two big ice sheets. Scandinavia was covered in ice. A lot of the Arctic Ocean was covered in ice. So over very long time scales, there are extremely large changes in the ice cover. This actually we can reconstruct in climate history, and what looks like a really noisy time series here, this is a reconstructed temperature on this axis and millions of years here. What looks like a really noisy time series actually has a very regular cycle. And these cycles are related to orbital changes. The way the Earth goes around the sun has changes on cycles of 40,000 years, 100,000 years, and so on. If we zoom into the last 500,000 years, it looks like that, and you see a very regular 100,000 year cycle. When I started studying glaciology, this was the view of ice sheets. These things change, they come and go. It takes hundreds of thousands of years to do that, but it's all very, very slow. So in terms of, for example, sea level rise, nothing to worry, right? So if you look at the early assessment reports from the Intergovernmental Panel on Climate Change, this is in the early 1990s, these were the kinds of predictions they made. So if you look at the scales here, we have on the axis here 25 centimeters of change by the end of 2100. And if you look in total here, this is the total change. A good part of that is just the oceans expanding because they're getting warmer. And then there is also a pretty good part from the mountain glaciers because they're all melting. That was acknowledged in 30 years ago already. But the ice sheets, not so much. Greenland is losing a little bit of mass. Antarctica apparently is going to grow over time because there's more precipitation there as it gets warmer. Well, actually, by now we're here. So you often hear in media, oh, the climate scientists, they always exaggerate. Well, they didn't. They actually underpredicted the amount of sea level rise that is happening. And one of the reasons for that is Greenland, because Greenland is losing mass way, way faster than we thought, because we always thought these ice sheets, it's going to take some orbital cycles before they start growing again or before they decay more. And Antarctica, actually, the story is the same. This is a time series from a satellite that literally actually weighs the Earth, measures the gravity from the Earth. And what you see here is that there's this kind of seasonal cycle of snow falling on the ice sheet and then melting in the summer. But overall, we've lost in this time series already more than 2 centimeters of global sea level, like raising the sea level over the entire Earth by that amount. So this is about an inch. These mass changes mostly happen at the margin, everywhere where it's dark red here, and I'll come back to that. Greenland didn't get that memo about slowly changing. In the early 2000s, we started seeing scientific articles and observations of very, very rapid change. This is one paper that was pretty well known of a change in a glacier where the glacier started speeding up by a factor of 2 or more. I'll get to that. Rapid changes in ice discharge from Greenland outlet glaciers. Acceleration of Jakobshavn Isbra triggered by warm subsurface ocean water. So this is all kind of early to mid 2000s. Everybody, when the next assessment report of the Intergovernmental Panel came out, they had to add a footnote and say, wait, things are changing in Greenland faster than we know. We don't know what to do about that in terms of prediction. The pattern we started seeing was a really interesting pattern. What you saw is that the glaciers are retreating. So this is a satellite picture of one particular glacier that comes in this way here. What you see out here is floating ice on the ocean. And the glacier front used to be out here. And 10, 15 years later, it was back 15 kilometers, 10 miles back. Really rapid retreat with just a few, within just a few years. With that retreat came, interestingly, acceleration. The glacier started moving faster. So if you look at these time series, these are different points on the glacier. As you move up glacier, it gets slower. And this is time in this direction. So what you saw in the 90s is speeds of 4,000 meters per year. This is actually really fast. This is the fastest glacier in Greenland. So everybody was like, oh, wow, 4,000 meters a year. This is fast. Well, a couple of years later, it was 8,000, 10,000, almost up to 12,000 meters per year. So these glaciers started going much, much faster. So with the retreat came acceleration. And then the third part that we started seeing with that acceleration, because it carried all that ice downstream, came thinning. This black line here is the glacier surface in the 1990s. In 2006, we're thinner by, look at the scale here, these are 500 meters. We're thinned by over 100 meters in just a few years of ice that has just disappeared. So there's this interesting pattern of retreat, acceleration, and thinning. And we could ask, well, haven't we seen this before? And the answer is yes. If you went into the literature, there were people like Austin Post here, who is actually has an honorary doctorate from UAF. That's the only degree he has. He never even finished high school, but he figured out how glaciers work. And he figured out this pattern of retreat, acceleration, thinning in Alaska. So this is a very fundamental paper for us, actually, fast tidewater glaciers. This is one that came a bit later that really laid out the mathematical model for that. And I won't get into that, but I'll show you some examples. Some of you might be familiar with Columbia Glacier outside Valdez. Well, Columbia Glacier in the 1980s was grounded out here by Heather Island. This is the glacier that produces the icebergs that the Exxon Valdez tried to get around and in a bad way. In the 1980s, the glacier was out here. In 2014, all that ice disappeared. That entire fjord opened up. Now, that ice where it says main branch is gone too. The west branch is almost entirely gone. We lost an entire glacier system in just since the 80s. This is like well within my lifetime, right? Not something Amy can say, but we have similar examples in other places. Glacier Bay, which you might also be familiar with, town of Gustavus is out here. This is a reconstruction that Chris Larson, who's here at UAF, did in his PhD of how the ice used to look like. This is how it looks like now. There's over 100 miles of retreat of ice here and thinning of over a kilometer. So really, really rapid changes in just 250 years. This is how it looked like from the ground. This is a repeat photo 60 years later, an entire fjord that opens up. So you can have really, really rapid changes. That's the lesson from Alaska. And that's what we're trying to apply to Greenland now. Like, so how does this glacier retreat, flow acceleration, and glacier thinning work? And when does that feedback stop? Like, how far can you go towards disintegrating the ice sheets rapidly? The other thing that I haven't talked about is it turns out that warm ocean waters play a big role in triggering that sort of stuff. And I'll come back to that a little bit. Let's go to Greenland now. Sermeck-Kujashek is in the older literature known by its Danish name Jakobshavn Isbrae, and I will switch back and forth a little bit. It's the fastest flowing glacier in Greenland. It can flow as fast as 30 meters, even more per day. This is not what we generally think of as glacial pace. It does have high seasonality in flow. We'll get into that. And it drains a good part, 6.5% of the ice sheet. So it's a really important glacier. That's why it's been studied. Just to orient yourself here a little bit, this part that's circled in blue is actually not glacier. That is floating ice. We call it an ice melange. It's just a mixture of icebergs and sea ice that's clogged in the fjord. And the actual fast-flowing ice, everything back that's white, that's outside that blue circle, is the ice sheet. Within that ice sheet is that really fast-flowing ice stream. It's sort of embedded in that. There will be images later where you can see that a bit clearer. This is just a compilation of how the velocities look like from space. And again, just to point out this bright red area, this really fast flow that drains a whole bunch of the ice sheet here. There's a long history of research, and much of it involves UAF. In the mid-'80s, my mentors, actually my PhD mentors, Keith Eckelmeyer and Will Harrison here, they work at Jakobshavn Isbrae or Sermekujashek. They found out, for example, through seismic reflection studies, that this is a really, really deep buried fjord there. That's why this flows so fast. There are a bunch of additional papers, some involving, you see the names of Eckelmeyer and Harrison coming up again. I got involved in the mid-'90s, actually, just before I started grad school here. I had an opportunity to go to the glacier with them and then work on this during my PhD and postdoc. And then as the glacier started accelerating, we got new projects funded to look at the acceleration and retreat. Jason Amundsen was my PhD student at the time, so he did his PhD. He ended up being Amy's undergraduate advisor. So we have like 4 generations of scientists studying this glacier now. I just want to point out before I hand it over to Amy, the same pattern that I've already mentioned, the terminus retreat, acceleration and so on, happen on this glacier. Here's the retreat from just a repeat photo. You see the glacier all the way back here in 2007 when it was all the way out here 10 miles further advanced just a few years earlier. This is something similar to what I already showed. We have acceleration. This is the speed profile as you go up glacier. This is the speed in the 1990s, and this is the speed in the early 2000s. You see more than a factor of 2 change. So this is going much, much faster. And here is another illustration of the thinning. And again, the thinning rates here, this is over 20 years, but most of that happened in 10 years or less, over 200 meters. This is about an LV building every 3 years that just disappears over a huge area, right? These are many tens of kilometers in extent. So when that ice accelerates, the way, this is a time lapse that just puts 1 picture a day together of the glacier flowing into the ocean. And what you see, you'd think that if the glacier accelerates, it should be advancing, but that's not what happens. It just breaks off into the ocean and it gets lost. And what you see here is just a lot of small things breaking off, but actually a lot of what happens is under the water. There's a lot of melting going on from the warm ocean because most of the ice, just as in the proverbial iceberg, is hidden, right? It's under the water, and that's where really a lot of the action is. There is actually a demonstration of that. This is a bunch of maps put together. This is West Greenland in gray here, and in blue is a reconstruction of ocean temperatures. And what was noticed is that in the late 90s, these blue colors indicate colder water. Warmer water started arriving from the south. This is the Erminger current that started pushing up north. And right when it started hitting Disco Island here, Disco Bay, where Jakobshavn Isbrae is, you started having the breakup of the glacier. So it was very clearly triggered by warm ocean water. This is how it looks like at the front of the glacier when these big calving events happen. This was a real surprise to us when we first saw it because they hadn't been documented before. But what you see is the glacier coming in from the right here and then breaking off in these huge overturning events. And just to give you an idea of scale, this whole iceberg, that's about the West Ridge of campus here on top of that. So think of the entire West Ridge just within a minute. So now we're getting to minutes or second time scales. Just the entire West Ridge just turns over, right, upside down. It's an unbelievable event to witness. The first time we saw that, you can't even really fathom what's going on in front of you, right? But when we look at the actual mass loss, we sort of see 2 components. One is the one I just showed you that's going on at the front. That's all the calving and the melting underneath. The other one is on the surface. And that's pretty easy to understand. If it gets warmer, there is more melt and the glaciers go away. But these 2 things play together. If we put that all together, kind of think of this as the mass loss of the glaciers over time, all the glaciers put together around Greenland, you see that there is that this starts picking up really quickly here, but there's also a really large seasonal component. And the seasonal component gives us a natural experiment, because instead of just waiting 100 years until it's a lot warmer, we can just look at the differences between winter and summer, because we have all these changes from very cold to quite warm happening within single years. And we see a lot of these processes happening on these seasonal timescales. So this turns into a really complicated problem, though, with lots of things playing against each other. So if you're a professor and a problem gets too complicated, you hand it off to your grad student. So that's what I'm going to do now, too.
So a lot of the seasonal changes that you might expect to think about on glaciers are the melt that happens at the surface, and then on tidewater glaciers it's a little bit different because you also have warm ocean waters that can melt where the ice flows and comes into contact with the water. There's also a lot of other feedbacks that can happen, and that's what we're really interested in. We know that there's thinning and there's retreat, but it's really the acceleration that drives a lot of the mass loss in Greenland. And so we're trying to think about how these different processes impact how the ice flows. One way that changes at the ocean impact velocity, it has to do with how the ice flows and terminates in the ocean, where it terminates, and how the ice is resisted, how that ice flow is resisted by the bed and by the sides of the fjord. And so what we see, a lot of patterns that we see around Greenland, are that in the wintertime, you have a seasonal advance of the terminus, and this tends to be a bit more stable, so the ice will slow down. Then the glacier retreats in the summertime when warm ocean water comes in and calving increases. And then the glacier speeds up. And then it will slow down again when the glacier re-advances. Another seasonal signal that we see is that melt occurs at the surface. It drains through crevasses and moulins and reaches the bed. And at the bed, there's a lot of sliding that happens. The ice flows over top of bumps and over the bedrock. And so in this top panel here, you can imagine there's no water at the bed. The ice is sliding right against the rock. And so there's a lot of friction there, and the ice flows slower. But once you start to add water, it forms these pockets and cavities that decrease the friction at the bed and allow the glacier to flow faster. So when there's more water, you'll see more flow, and when there's less water, there won't. There'll be less. That's not always the case, though, because over time, with enough meltwater reaching the bed, these large channels can form, and these rivers of water underneath the glacier can evacuate the water. And we're very familiar with that here in Fairbanks. This is the Kastner Ice Cave in the summer, where you can see a lot of water being drained through this one area of the glacier. And these channels look different, obviously, on tidewater glaciers. We can't actually go and observe how much water is exiting the terminus of the glacier, but this is a video of LeConte Glacier, where you can see there's obviously a lot of water moving out of this system. It's not as easy in Greenland because there's a lot of ice in the fjord, and so we can't actually see a lot of the meltwater that's coming up. But because of channels, there's kind of this interesting relationship with velocity. Earlier in the melt season, we have a lot of water reaching the bed. We see glaciers often speed up. And then once channels form and an efficient drainage system develops, you can actually see the glacier slow down. But both of these things often happen at the same time. We have warm ocean water and warm air temperatures. And so both of these processes happen together, and what we observe at the surface is a combination of the two, maybe this purple line here. And so what we want to do is really try to understand what processes drive glaciers to speed up seasonally, and can we figure out how much these different processes might change in the future, say if air temperatures around Greenland increase. And the tools that we use to think about some of these problems are obviously just going, like Martin has said, we go to Greenland and observe the changes that we're observing there in the field. We can also use satellites and learn a lot from satellite imagery. And we can use observations together with models to try to understand the physics of what's happening. And we can get really specific about what processes are happening in these really complex systems. But that's really hard to do at really large scales. So often we have kind of simpler models or models that account for simpler processes and run that on the scale of ice sheets and try to get better projections of mass loss and sea level rise. And so I'm going to tell you about what I've actually been spending most of my time on my PhD for a very short time tonight. But the reason that we have to use models when we're thinking about especially meltwater at the bed is because it's extremely hard to observe that environment. And so we need to use our understanding of the physics that are dominating these systems to try to understand what's actually happening. It's kind of challenging because we have to model ice flow and water flow together. And ice flows very fast in these very large tidewater glaciers in Greenland, but it's still very slow compared to the flow of water. If you think about water melting 50 kilometers from the terminus, it might arrive, if it melts here, it might take a day, hours to days to arrive at the terminus, whereas ice at this location might take decades or many decades to arrive. So it's very computationally difficult to kind of think about all of these processes that are really tightly coupled on, in both of these systems. So this is a 2D view of the glacier bed, just to show you some of the things that we can do with our glacier models. This top view shows in the color the bed topography. So you have like a trough like you would see in a fjord. And then there's these black lines that represent these channels or these rivers that form underneath the ice. Then we have the sliding speed. So this is how fast the ice is moving that's in contact with the bed. And then there's some water that is between the ice and the bed. And then water pressure, which is very strongly linked to how fast the ice flows. And what we can do is force some amount of water to reach the glacier bed. This is day of year, so looking at the melt season, and we can see how water pressure and ice speed evolve over time. And what you see here in the top is around the middle of the summer, some channels start to form, and that actually impacts the velocity and causes it to slow down, like we have seen in the kind of schematic earlier. Won't linger too long on that. I'm just going to talk now a little bit about some of the work that I've been doing with an undergraduate student, Tegan Silva, at UAF, looking at what we can learn using remote sensing over multiple years. So this is a radar image. You saw a similar image earlier. This is geologic. And you can see really nicely in this image these flow lines. So ice is flowing here to the terminus. And what we can do with a radar image like this, it can see through clouds, so we can get a lot of different snapshots in time of where the glacier terminus is. So the ocean's out here, the terminus is here. So we can draw these lines to see where the terminus is at a given time. And there's really large changes between winter and summer every year. So in winter in 2018, the terminus was here, and then it retreated back here in the summer of 2018. And we can do this over time and have a lot of different terminus positions. And so this is showing where the terminus was at from 2018 to 2021. And you can see that it has advanced, this is down, and then retreated, advanced, and retreated over time. And what's nice about having a longer time series than just going to the field 1 or 2 years is you can actually see a lot of variability from year to year about what's driving these different things. So in this year, in 2021, we didn't have a re-advance of the terminus like we have in previous years. So it provides a really nice experiment to say, okay, well, what happens if you don't get terminus retreat? Can we learn something more about what's happening with meltwater? So this is runoff over that same time period from a climate model. So we can just think about how much meltwater is getting to the bed of this glacier catchment. And then we really want to think about ice flow, right? So we want to think about how these processes, these different variables, impact how fast the glacier flows over this same time period. So I'm going to show you some figures that show the velocity at these different points along the glacier. So this is the same at the top, the terminus retreat. We have meltwater here in the middle, and then this is the speed along the center of the glacier where the purple is closest to the terminus. And you can see this is flowing very fast, and there's a lot of variability from year to year. But what's really clear is that for especially the fastest flowing ice in purple, we see it really closely follows the terminus dynamics. So when it's retreated, that's when we see this speed up. And that's later than when we would see like runoff. So we can think, this makes us think that it's a lot more closely related to terminus retreat. You can also see that very clearly here, where it doesn't really slow down that much in the winter when the terminus doesn't re-advance. This is up higher on the glacier to the south, and you can see this is slower speeds now, but it much more closely aligns with the timing of meltwater as opposed to terminus position. And so what we've found using time series analysis is that we have a lot more, it's much more related to terminus, retreat and advance, the ice flow, the seasonal ice flow dynamics near the terminus, and in the south, where I just showed you, it's much more runoff driven, and up higher, it's a combination of both. And while remote sensing is great, and you can learn a lot because you can get a long time period and you can get a lot of different sites, or think about a large spatial area like you can't do in the field, you can't get the really small, short time scales. You can't look at sub 2-week periods like hours and days. So I'm going to let Martin tell you a bit about our field.
Yeah, so we went back to the field to look at these kind of faster timescales. So this is, we put a proposal together for NSF that was under the leadership of Liz Alti here, who is at NASA Goddard, and Chase Namonson's part of it, who was my PhD student and Amy's undergraduate advisor. We went back to Ilulissat. That's a town at the entrance of the fjord here. Pretty small town, about 5,000 people, and about as many dogs. It's dwarfed by the fjord outside town. So town is up in here, and this is the ice fjord. So this is floating ice that's coming out here. These big icebergs, some of them are almost as big as town. They get hung up on this bench, which is an old moraine that is, it's underwater, but it's pretty shallow, so the icebergs can't make it across. So they sit there, and then the ice piles up behind it. This is getting to be a pretty good tourist attraction, too, because they come to see the ice there. A lot of it is really kind of reminiscent of Alaska. You see lots of dogs that like to pose. You see icebergs, although the icebergs are definitely different than the ones you would see, say, in Southeast Alaska. They're huge. You see fishing boats in people's yards. Fishing is a big part of what Greenland does. A lot of people live off fishing and fish right between those big icebergs there, because that's where there's a lot of halibut, for example, one of the big fisheries. A lot of the things you'd love about Greenland is the things we love about the Arctic anywhere, the beautiful light. The nicer thing is they have a little bit nicer style of houses with the Scandinavian colorful houses. The icebergs are just enormous, right? So you see these big things floating by that are bigger than city blocks. There's actually a person in this image for scale. So these are really, truly enormous things. And really, the name Ilulissat actually means city of icebergs. So it's very much part of the identity of that place. So we went back there to do observations, and actually a fairly basic observational program. One of the things we're doing is just put up cameras to take pictures every hour to see what the glacier front does. So these cameras look out onto the fjord. Jason, in a very stylish 70s suit, is installing the camera, and I'm doing very important supervising. With that, you get these sorts of pictures. This is just one picture a day, and what you can see here is the glacier front, And you can see the ice coming in from the right here, and then every couple days, the front steps back, right? Now it's here, now it's here, and that's when these huge calving events that I was showing earlier that are kind of the size of UAF campus happen, right? And the glacier steps back, keeps flowing in again, steps back, and that repeats itself the entire summer. We use these pictures then to turn the sound off here. We use those pictures then to track the front, like Amy was describing from satellite images, only at much, much higher frequency. This is just from a helicopter flight going onto the glacier. We want to measure how fast it flows. This is really tricky to do on the surface. If you look at the surface, it's extremely crevassed and it changes very rapidly. We've done this before, but you put targets out there and within a couple of days they fall over, right? So in this project here, we actually went up higher up the glacier. These are the points where we started putting up GPS stations. Again, there's points along kind of the main glacier here, and then we have a line from the north and a line from the south. We were particularly interested in the south because those blue things you see here, those are lakes. They form every year on the surface, and as Amy will show you in a little bit, they drain occasionally. You want to see the effect of that. When we went up there, we landed. We went far enough up so you can actually land a helicopter, and we drill in various poles to put up GPS antennas. We have to drill them in about 4 meters because the ice melts during the summer. And we leave something like this behind. You see on the right here, the GPS antenna. This is buried 4 meters into the ice. There is a contraption here that measures melt, various things that measure temperature and some weather variables like that. This is how it looks like when you fly away from it. So it looks much better than lower in the glacier in terms of safety, but there's still crevasses everywhere, as you can see. We're flying over. So we're probably 30, 40 kilometers away from the glacier front now. Still very torn up area, lots of crevasses. So definitely a challenge to operate safely. These stations, over time, they move. So if you want to go back to collect the data, you got to account for that because they're not going to be where you started out. This is just plotting the positions over time for the summer. And when we come back, this is the prediction we did. The blue ones is where we put the stations, and the red ones is where we found them again. Finding them is not always trivial. This is how it looks like. It's good to have a pilot with good eyes. So you have to pick out these stations here that are no longer where they used to be, and you try to find them from the air, from a rapidly moving helicopter. This is how it looks like on the ground. So this antenna that used to be right at the surface is now sticking 2 meters more out because the whole glacier surface has melted during the summer. We get time series from that. For example, this is just a time series of melt over time at the top, temperature over time at the bottom. We get velocities from the positions that we have. We measure the velocity of the glacier. And this is the time series we're going to look at really closely, how that relates to things like temperature and melt. But again, that's the hard part, so I'm going to again pass it off to Amy here.
So we haven't looked too much at this data, but we're just going to present some interesting things that we found from last summer. You'll first notice these blue spots on the glacier in the center. It's moving the fastest there. And you have these slower regions off to the sides. But what you'll notice is there's a lot of variability at all the sites and some really significant events here in green and here in blue. And so one thing is that we're not actually interested in the speed itself. We're interested in the change over time. So we've normalized it by each point's speed. So all we're doing is looking at the change from the beginning of the summer and how that changes over time. One thing to point out is that you see this speed up at this blue site. You see the glacier speeds up. That's related to the retreat of the terminus. That effect is less dominant at other sites. But there's some other interesting things I'm just going to point out. There's this pretty consistent pattern that we see during this week in July. And if we zoom in on that, this is the process that I was talking about earlier, where when there's more melt, there's more sliding. And so this bottom panel is the normalized temperature, so temperature at all these different sites over time, and then the speed on those days. And you can see when the temperature increases, melt occurs, and shortly after, you see this speed up in velocity. We can also, I just want to point out this is what we can get from remote sensing. So we get terminus positions over time. In 2025, we saw a 4-kilometer retreat from May when we put out our sensors to September when we picked them up again. And the largest retreat in a 2-week period over that record was 1,300 meters between June 27th and July 14th. And if we only had satellites, this was the best that we could do. This is all that we would know about that time period. But because we have a time-lapse camera, we can get down to the hour of when these calving events happen and see how that impacts velocity. So this is on July 1st, 4:30 a.m. This is the terminus. And within an hour, we see this really large calving event. A few hours later, it's kind of around the same position, and we have another really large calving event. You can even see the spray. So these are the types of things that we can do with the time-lapse imagery. And we can look at, okay, when did this calving event happen, and how did the ice respond at these different sites? Another really interesting time period is towards the end of the summer, when there's a lot going on. First, I'll just point out in the temperature, which we can think about as a proxy for melt, we have this kind of regular increase and decrease above 0 and then drops down below 0 in this early part of the series. But then on August 17th, it doesn't cool back down. We have this period of really high temperature and high melt. And then we see the glacier speed up, especially along the center line, and then at other parts of the glacier as well. And what's interesting is on August 18th at 2:30 p.m., between 2:30 and 3:30, we see a really large calving event. And actually, it's retreated so far out of the frame, we can't actually see the change in terminus position, but we can see the movement of a lot of ice in the fjord, and this blue ice here is indicative of a very recent calving event. So this happens at 3 p.m. Right after we see high melt. And then we have another interesting event here in the time series. So remind you, this is where our sites are at. This lake here is larger than Birch Lake, so it's a lot of water, right above where the ice is flowing, and to our nearest sites, 12 kilometers away. So on August 23rd, we can use radar again. Doesn't matter what the weather. We can see that there is this lake I was just talking about. It's full of water. And August 28th, a lot of that water has drained. A lot of water in other lakes has drained as well, if you look between these images. But what we see is when that lake above our field site drains sometime between August 23rd and August 26th. And that's when we see this really dramatic increase in velocity on those southern sites in green. So there's a lot of things happening all at once. Even when we get down to really short time scales, it's still really hard to disentangle what processes are impacting velocity. But we have a lot of information from around the glacier, and with our time-lapse and our melt data, we can try to tease these apart, which I guess will be my job soon. And like Martin was saying, we've learned a lot about Greenland Tidewater glaciers from the work that's done on Alaska glaciers. We can also learn a lot about Alaska glaciers from what we know about Greenland. This is Sit Klein, or Hubbard Glacier, close to Yakutat. And this glacier has a really dynamic seasonal signal. These are velocities that speed up to 5 kilometers per year and then drop down to 1 kilometer or even less. So when it's purple, it's very slow, and then in the really light colors, you see really, really fast flow. And there's lots of interesting things about this glacier, but the seasonal signal is really clearly related to very different variables at different times of the year. So we're thinking about that as well. If you're interested in learning more about tidewater glacier change in Alaska and Greenland, come see our exhibit at the Museum of the North, which will be opening October this year. And with that, I think we'll take questions.
Thanks, Amy and Martin. I think maybe I have a coworker out there somewhere who will help me with the other mic, but I can get things started. Are there any questions from our in-room audience? Just raise your hand, I'll bring you a mic. I see you, Mark Conde, I'm coming back.
So we hear that with these ice sheets like Greenland or West Antarctica, the melt causes water to get to the base and lubrication, and they talk about a collapse of the ice sheet. So what does that look like, and what are the timescales that would be involved in a large-scale collapse of an ice sheet? Is that something that takes decades or centuries, or how does that look?
So the reason these things are unstable is because they're grounded so far below sea level. So West Antarctica is actually the one place you have to worry most about sea level is the West Antarctic ice sheet, particularly the Amundsen Sea sector there. And the reason is that the base of the ice sheet is in some places over 2,000 meters below sea level. And the glacier bed actually deepens as you get away from the front. And you can get that feedback I was talking about, that acceleration, retreat, and thinning, that can be sort of a self-defeating feedback where the glacier just keeps retreating just as it did in Glacier Bay. So that's the worry. And the worry is that in West Antarctica, in places like Thwaites Glacier that you hear about in the news, that process might already be well underway. That's actually still a debate. Right now, the consensus maybe is that that's true, that over the next 1,000 years, West Antarctica will disappear. That's almost unstoppable. It's not so clear how much of that will happen in the next 100 years. People are still arguing a lot about the timescales. But if we see, again, the Alaska example is that retreat can be rapid, like, a kilometer a year retreat. And we see grounding line retreats, so the place where the ice meets the underground in areas of West Antarctica that are on that same rate, like a kilometer of retreat per year. So really, really rapid changes. And that, down there, we were quickly talking, Thwaites Glacier alone is 60 centimeters of global sea level, just one single glacier. So that's the real concern for rapid sea level rise. Is Greenland also a little slower and a little less, because there the deep ice is constrained to individual fjords, not entire huge basins. Most of Greenland, if you take the ice off, is going to be above water. But Antarctica, if you take the ice off, West Antarctica is almost entirely underwater. I don't know if that answers the question. But
All right, any other questions in the room?
So when there are those big calving events and the big icebergs break off and they flip, why do they flip?
Yeah, that's an interesting question. It's basically because the way they break off, they're deeper than white, so they're not stable. Right? They're sort of upright in the water like that, so they'd like to be like this. So that's why they break out. And it's also, Jason actually in his thesis did a bit of work on that. The ice that's out in front, the sea ice and all that, puts a little bit of force on it as well. So they preferentially actually break out this way, towards, away from the front bottom. We always see that. Yeah. But they're basically, it's just, if you had an ice cube is pretty stable in the water, but if you had an ice slab in the water and you put it upright, it's not very stable. It wants to be on its side. That's what happens. So the interesting thing about that, if I might just add, is that when that happens, when that thing comes lopsided like that, the part you see is actually the part that used to be vertical. So you actually see the bottom of the glacier come up, right? When it hits the water surface, that's the stuff that was at the very bottom of the fjord. It was almost 1,000 meters deep just minutes before, and it's now sitting on the surface. That also, there is no other event in the ocean that mixes up an ocean so rapidly, right? Within 1 minute, you sweep through almost 1,000 meters of water. Really dramatic events. The energy involved is about the same as that of a nuclear explosion, just over a longer time, but super energetic events. You can measure those in seismometers. When one of these events happen in Greenland, you can measure it anywhere in the globe.
Okay, so when you put out your field stations out onto the glacial ice, how can you expect that it won't fall or be sucked into a crevasse? Or how do you maintain it, and how often do you go out to the stations? And like, what if you just lose all of that gear to the glacial ice? I can imagine that can be pretty problematic.
Yeah, so we don't have to maintain it once we set it out. There's solar panels on top, so it has power throughout the summer. We do worry about it falling in a crevasse. We have a lot of PVC and duct tape that just kind of makes the surface area a little bit bigger, so it can stabilize it a little bit from turning over. But yeah, there is the risk that a crevasse will open up right where our station is. That's the size of a helicopter, right? That's obviously going to fall in. And there were some crevasses that opened up really close to where our sites were, which made it very hard to land the helicopter and get out and safely collect our instruments at the end of the year. But when we're choosing our sites, we're also trying to see, where are these GPS going to be, easy to get later in the summer.
I can read some online questions. We have lots of questions from our online audience. And we have folks joining from all over Alaska, the lower 48, Japan, and British Columbia. So good representation. Nancy on Zoom has a very intriguing question. Has Earth passed enough tipping points that humanity should leapfrog mitigation and adaptation to commence geoengineering to cool Earth for a few centuries?
This actually I mean, it's an interesting question, right? Like at what point should, my personal opinion is that we know the solution to the climate crisis, right? We're putting way too much carbon into the atmosphere. And I think there is no dispute anywhere in the scientific community that if we were to stop doing that as rapidly as we can, that would help stabilize the climate. And maybe I think we're also at the point where we actually have to really actively think about carbon dioxide removal from the atmosphere, which is also a form of geoengineering. The other forms of geoengineering, there's a lot of discussion. I can't really speak to the solar radiation management stuff as an expert. I have my opinions on that as well, but that's not the field I study. But there are geoengineering approaches that supposedly, there is ideas that you could pump water away from the base of the glacier to make them slower in Antarctica, so they wouldn't flow into the ocean so rapidly. And they're actually now being relatively seriously discussed, and there's no other ways of saying this. They're bonkers. The scale of what is needed there. First of all, it is far from clear whether it would work. It might very well. If you could actually remove enough water, there's a variety of reasons why that could have the opposite effect. And the logistical challenge. Just keeping a GPS station working in Antarctica over winter is a challenge. Like putting up pumps that would use on the order of tens to hundreds of megawatt of energy to operate continuously on the Antarctic ice sheet through winter in an area where we can't even get to every year. because of ice. It's just not a realistic solution. And then the governance issues, like who decides to do that, who pays for it. There's just so much that's not working with that idea. There are others, like people, I mentioned warm ocean water. There are proposals how to build sea curtains that keep the warm water away from the glaciers. But if you just think about the ecological impacts of doing something like that, of actually altering ocean currents. So I have to say, not everybody thinks like I do on this, but I think this is not the right way forward. The right way forward is to address the problem where it is, right? And the idea that the international community is going to come around geoengineering when they can't come around something that we know we need to do, that seems far-fetched. The thing with solar radiation management and things like that is that single nations or single players could actually start being active, right? Like people could start putting particles into the stratosphere sort of as a single country could decide to start doing that. But all of these things have global implications, and I would say we just don't understand this. Engineering implies that you understand the system to a degree, right? You do something because you want to have a specific effect. I don't think we understand climate to the degree where we can do global intervention and have any hope of predicting what exactly is going to happen. So I have a pretty dim view on that myself. But it's a fair question for sure.
We have a follow-up in-room question.
Thank you very much, and you probably may have just answered it, but I was going to ask the question is do you have a prediction on when this cycle is going to reverse? I'll use the example as the Norsemen, the Scandinavians that had settled in Greenland. They were not fishermen. They actually raised sheep, and they were the diaries where they talk about where the sheep were so weak because the winters were so long they have to carry them out there to the fields before the sheep couldn't survive, so that's when they vacated Greenland. And that was about the 900s to 1000s. I just say, so it went from a very warm part of Greenland to incredibly cold in less than a lifetime. So that was kind of the question is when do you think this cycle would flip again? Because I would suspect it would be solar radiation based versus carbon based in that regard, because the sun would have been heating it up at that time. So that, back to the question is have you done any analysis or any predictions on when you anticipate the cycling flipping again? Thank you.
Yeah, the short answer is no, I haven't. What we see, if you look at past climate records, you see that temperature changes can happen really rapidly, especially coolings can happen over very, very short time. Some indications in Greenland ice cores are that over a few years you can drop climate really rapidly. Warming is less clear, and I might have to go all the way back here, but there's something really interesting and I don't think entirely understood about coming out of the last ice age, which is, I have to go to basically the first slide here, so sorry. There's probably a quicker way of doing this. But when we look at the climate records, this is literally the first slide I showed. Here, if you look carefully at the very most recent time here, this is the Holocene here. So these are the last 10,000 years. So when we came out of the last interglacial, it didn't get as warm. These periods before were warmer, the interglacials, than it is now. And I don't think it's entirely clear why the Holocene is where it's at. Also, not why it's so flat. Some climate historians refer to the Holocene as the boring Holocene, because you have these large. Oops. Oh, we might have just lost Zoom. Well, that stops the questions there. Yeah, so it's not entirely clear why the climate was so, even with all those changes that you're addressing, like what happened in Greenland during the Little Ice Age and so on, these changes are much, much smaller than what Earth shows us that can happen in the long term. And why the Holocene is so, and this might also give us a sense of false security, because 10,000 years, that's the entire period of human civilization. We have not seen really dramatic climate events since humans started basically being agricultural society, right? So we're playing with fire here, right? Like we're tickling a system here that we know from the past can undergo very rapid, very large changes. And I think it's only fair to say that we have no clue what we're doing. We're in this period of stability. We're pumping CO2 into the atmosphere like there is no tomorrow, and hoping for the best, essentially. So it's not a comforting thought. But yes, right now the question is like when are you going back down from the orbital cycles? But again, this is, I remind you, this is a 100,000 year sort of cycle. So even this time span here is more than 10,000 years. What we're doing now to the atmosphere, that forcing is something that happens in decades, right? It happened within a century, essentially. So we're talking much, much different timescales.
Two people online asked pretty much the same question, Ken and Peter. And I'll read Ken's question. Explain what changed with the ocean flow and the arrival of the warm current. Is the current new?
The current that in itself is not new. It's an offshoot of the Gulf Stream that actually influences climate everywhere, right? That's what makes Europe's climate relatively mild for the latitude, because it's warm water that comes out of the Gulf of Mexico. But some of that hits the coast of Greenland and then travels up along the west coast. What was new is that, and I actually can't speak with authority on that, what caused that, but in the early 2000s, water started migrating up the coast, and you could see the glaciers change, both on the east and west coast. You could just see the change traveling north as that water came north. So and Iuliset and Sermekuyashek, they're at an interesting point where you have cold water coming down from the Arctic, from Baffin Bay, and you have that warm water coming. And you even see sometimes the cold water pushes a little further south, and then you have a little less change on the glacier, and then it pushes north again, and you have a little more change. But that's oceanography. I'm not an oceanographer, so I don't exactly know what the driving forces are there. Yeah.
Anyone else in the room? Or I'll ask one more question from online folks. Okay. Maybe this is a question for Amy. No pressure, but maybe. Where did it go? Oh, is there a reason why we see ice flow rivers embedded within the larger glacier field? Like, why is there kind of one river of ice in the middle? Why does that happen?
Yeah, well, it isn't necessarily like that across the whole glacier bed, but there's some feedbacks that happen with large channels where there's much lower water pressure, so it drives a lot of that high water pressure, water in higher pressure regions to that main channel. So we see really large channels at the terminus, and then as you move up glacier, you see smaller channels, and they might become a bit more braided, kind of like we saw in that video. But often on land terminating glaciers, you see there's a lot of melt that's happening near the terminus. So you're also adding a lot more water there, and so maybe it's not just one big river that kind of travels all the way up the glacier.
Okay, thank you, Amy and Martin, for your wonderful talk and for answering all those questions.